brain-inspired architecture. Neuromorphic computing is a transformative approach that reimagines how machines process information, taking inspiration directly from the intricate architecture of the human brain. And at its core, this brain-inspired design seeks to replicate the network of neurons and synapses that enable our minds to think, learn, and adapt with remarkable efficiency. Imagine a computer not as a cold binary machine that performs calculations in a linear sequential manner, but as a dynamic system built to mimic the billions of interconnected neurons in your brain, where each neuron communicates with thousands of others through a complex web of synapses, processing information in parallel and responding to new stimuli with flexibility and speed that far surpasses traditional architectures. In neuromorphic computing, engineers design hardware that mirrors this natural system, employing artificial neurons that fire electrical signals and artificial synapses that adjust their connection strength based on experience, just as our biological counterparts do, enabling systems to not only process data more efficiently, but also to learn from the environment in a way that is inherently adaptive and context-sensitive. And it is this very paradigm shift that holds the promise of revolutionizing the way we interact with technology. At the heart of this brain-inspired architecture lies the concept of parallel processing, a stark departure from the sequential operation of conventional computers that rely on central processing units, CPUs, to execute one instruction at a time, no matter how advanced the chip may be. In contrast, the human brain performs countless processes simultaneously, with different regions of the brain handling sensory input, motor control, decision-making, and memory, all at once. And neuromorphic systems strive to emulate this behavior by creating networks where multiple artificial neurons operate concurrently, each one performing a piece of the overall computation in tandem with others, thus achieving a level of efficiency and speed that is unparalleled by traditional digital circuits. This approach not only allows for the rapid processing of vast amounts of data, but it also enables the system to be remarkably energy efficient, because unlike conventional processors that consume power continuously regardless of workload, neuromorphic chips operate in a way that is event-driven, meaning that neurons only fire when they detect a significant change or a relevant input, thereby conserving energy by avoiding unnecessary computations, much like the human brain, which consumes only about 20 watts of power, while performing tasks that require immense processing capabilities. The architecture of neuromorphic systems is designed to reflect the hierarchical and modular structure of the brain, where different clusters of neurons work together to perform specialized functions, yet remain interconnected to share information across various regions. This modality allows for the development of networks that can be scaled and adapted for different applications, whether it's for image recognition, natural language processing, robotics, or real-time sensory data analysis. For instance, in a neuromorphic vision system, arrays of artificial neurons can be dedicated to processing different aspects of visual data, such as color, motion, depth, and edges. Much like how the visual cortex in the human brain segregates and processes these features in parallel before integrating them into a coherent image. This level of specialization and integration is what gives neuromorphic systems their edge, enabling them to perform complex tasks with a level of nuance and speed that traditional architectures struggle to achieve. Beyond raw processing power and efficiency, one of the most compelling aspects of brain-inspired architecture is its ability to support adaptive learning through mechanisms that resemble synaptic plasticity, the process by which biological synapses strengthen or weaken over time based on the frequency and intensity of their activation. In neuromorphic computing, artificial synapses are designed to adjust their weights the numerical values that determine the strength of the connection between neurons in response to incoming data, allowing the network to learn from experience and refine its responses to future stimuli. This kind of unsupervised learning is a game changer in the field of artificial intelligence, as it enables systems to develop patterns of behavior and make decisions without needing explicit programming for every possible scenario. By mimicking the brain's capacity to adapt and learn from its environment, neuromorphic architectures open up possibilities for machines that can autonomously evolve their performance, improve over time, and even generalize their learning to handle novel situations. A feat that is exceedingly difficult for conventional computing systems that depend on pre-programmed algorithms and fixed architectures. The potential applications of neuromorphic computing are vast and varied, and its brain-inspired architecture makes it uniquely suited to tackle challenges that require a blend of high-speed processing, low energy consumption, and adaptive learning. In robotics, for example, neuromorphic chips can be integrated into autonomous systems to provide real-time sensory processing and decision-making capabilities, enabling robots to navigate complex environments, recognize obstacles, and interact with humans in a more natural and intuitive manner. In the realm of healthcare, neuromorphic systems have the potential to power advanced diagnostic tools that can analyze medical images, monitor patient data, and even predict the onset of diseases by detecting subtle patterns in vast datasets, all while operating at speeds and energy levels that make them practical for continuous use in clinical settings. In the field of consumer electronics, the integration of neuromorphic processors into devices such as smartphones and wearables could lead to a new generation of smart, energy-efficient devices that are capable of real-time contextual awareness, personalized responses, and interactive experiences that adapt to the user's habits and preferences, much like a digital extension of one's own mind. Furthermore, brain-inspired architectures are also fueling a deeper exploration into the nature of intelligence itself, blurring the lines between biological and artificial cognition, and inspiring a new wave of research that seeks to understand not only how the brain works, but also how we can harness its principles to create machines that think, learn, and even feel in ways that are strikingly similar to human consciousness. This interdisciplinary approach, bridging neuroscience, computer science, and engineering, is leading to innovations that challenge our traditional definitions of what it means to be intelligent, and is sparking debates about the future of artificial intelligence, the ethics of machine learning, and the potential for machines to one day possess qualities that we have long considered uniquely human. By drawing inspiration from the brain, neuromorphic computing is not only pushing the boundaries of technology, but it is also inviting us to reconsider our relationship with machines, to envision a future where technology is not just a tool, but an extension of our own cognitive processes. In practical terms, the realization of brain-inspired architecture in neuromorphic systems involves a radical rethinking of how we design and fabricate hardware. Traditional computer chips are built on the premise of the von Neumann architecture, where the separation of memory and processing units creates a bottleneck that limits the speed and efficiency of data transfer. Neuromorphic chips, however, integrate memory and processing into a single unified structure, much like the brain does, where neurons both store and process information simultaneously. This integration eliminates the need for constant data shuffling between separate units, significantly reducing latency and energy consumption, and allowing the system to operate more fluidly and naturally. The design of these chips often involves the use of novel materials and fabrication techniques that support the dynamic, adaptive behavior of artificial neurons and synapses, such as memistors, which can change their resistance based on the history of electrical signals passing through them, mimicking the behavior of biological synapses. The development of neuromorphic hardware is not without its challenges, however, as engineers and scientists work to replicate the staggering complexity of the human brain, which contains approximately 86 billion neurons and trillions of synapses. Achieving even a fraction of this level of connectivity in silicon is an enormous task, and researchers are continually exploring new methods to scale up neuromorphic systems without sacrificing their energy efficiency or processing capabilities. One promising approach is to leverage advances in nanotechnology and material science to create ultra-dense networks of artificial neurons that can operate at speeds and efficiencies that rival their biological counterparts. Another avenue of research is the development of hybrid systems that combine traditional computing elements with neuromorphic components, thereby harnessing the strength of both approaches to create versatile systems that can handle a wide range of tasks, from routine data processing to complex adaptive learning. In addition to hardware innovations, the success of brain-inspired architectures also depends on the development of new algorithms and programming paradigms that can fully exploit the unique properties of neuromorphic systems. Traditional programming languages and models are often ill-suited to the parallel event-driven nature of neuromorphic computing, and new frameworks are needed that can handle the asynchronous, distributed processing of artificial neural networks. Researchers are actively developing such algorithms, drawing inspiration from the brain's own methods of information processing, such as spiking neural networks, where neurons communicate through discrete electrical pulses rather than continuous signals, and plasticity rules that adjust synaptic weights based on the timing and frequency of spikes. These algorithms not only enable neuromorphic systems to learn and adapt in real time, but they also open up new possibilities for solving complex problems that are intractable for conventional computers, such as pattern recognition, anomaly detection, and predictive modeling in environments where data is noisy, incomplete, or constantly changing. The journey to fully realize the potential of brain-inspired architecture is both challenging and exhilarating, as it calls for a fusion of disciplines and a reimagining of what computers can be. It is a quest to replicate the elegance and efficiency of the human brain in a machine, to create systems that are not only powerful and energy efficient, but also capable of evolving and learning in ways that mirror our own cognitive processes. This pursuit is driving a wave of innovation that is already beginning to impact a wide range of industries. From autonomous vehicles and smart cities to personalized medicine and advanced robotics, and it promises to fundamentally change the way we interact with technology in the years to come. As we stand on the threshold of this new era in computing, the possibilities seem almost limitless, and the potential applications of brain-inspired architectures are limited only by our imagination. Imagine a future where neuromorphic systems power the next generation of artificial intelligence, where machines are able to process and learn from data with a level of speed and efficiency that was once thought impossible, where your personal devices can intuitively adapt to your needs, and where the line between biological and artificial intelligence blurs to the point that computers become true extensions of the human mind. In such a future, the challenges of today, energy consumption, processing bottlenecks, and limited adaptability, will seem like distant memories, replaced by a new paradigm of computing that is as natural, efficient, and intelligent as the brain itself. This is the promise of brain-inspired architecture in neuromorphic computing, a promise that is driving researchers to explore new frontiers, to experiment with novel materials, to develop cutting-edge algorithms, and to push the boundaries of what technology can achieve. It is a field that challenges us to rethink our assumptions about computation, to draw lessons from the biological systems that have evolved over millions of years, and to apply those lessons in ways that can transform the digital world. Every breakthrough in neuromorphic hardware brings us one step closer to creating machines that not only process information more efficiently, but also learn, adapt, and interact with the world in ways that are remarkably human, opening up new opportunities for innovation and ushering in a future where the synergy between biology and technology creates a smarter, more connected world. In essence, brain-inspired architecture is more than just a design philosophy. It is a revolution in computing that seeks to emulate the very essence of human intelligence. It is an approach that recognizes the power of the brain's parallel, adaptive, and energy-efficient processing, and it strives to capture that power in silicon, creating systems that can learn from experience, respond to new information, and operate with a level of efficiency that defies the limitations of traditional computing. As we continue to explore and develop these innovative architectures, we are not just building faster computers. We are laying the foundation for a new generation of intelligent systems that have the potential to transform every aspect of our lives, from the way we work and learn to the way we interact with the world around us. Ultimately, the journey to replicate the human brain in silicon is one of the most ambitious and exciting endeavors in modern technology, a quest that has the potential to change the very nature of computing and redefine what it means to be intelligent in the digital age. By drawing inspiration from the brain's remarkable architecture, neuromorphic computing offers a path to systems that are not only more efficient and powerful, but also more in tune with the complexities of the real world, capable of processing information in ways that are adaptive, resilient, and profoundly human. And as we continue to push the boundaries of this emerging field, one thing is clear. The future of computing lies in our ability to learn from nature, to harness the principles that govern the human brain, and to create machines that can think, learn, and adapt in a world that is as dynamic and complex as the mind itself. Energy efficiency and speed. Energy efficiency and speed in neuromorphic computing represent a radical departure from traditional computing architectures, offering a glimpse into a future where complex tasks are executed with the elegance and power of the human brain, all while consuming a fraction of the energy and delivering rapid response times that redefine what we consider possible in digital systems. And it all starts with the remarkable concept of emulating neural processes, where artificial neurons and synapses work together in a highly parallel and event-driven manner, much like the biological networks in our own brains, to process information dynamically and efficiently, allowing systems to recognize patterns, interpret sensory data, and make decisions in real time without the energy overhead and latency that plague conventional processors. And this revolutionary approach not only promises to transform the way we design computers, but also holds the potential to address some of the most pressing challenges in energy consumption and computational speed faced by modern technology. Imagine a scenario where a computer, instead of following a rigid clock-driven cycle that executes instructions one after the other, is designed to operate much like the human brain, where millions of tiny processing units, artificial neurons, fire only when needed, communicating through synapse-like connections that adjust their strength based on experience. And this event-driven mode of operation means that, unlike traditional systems that waste energy by constantly cycling through instructions, regardless of necessity, neuromorphic systems consume power only when there is meaningful activity, thereby drastically reducing energy usage, while simultaneously achieving levels of computational speed that allow for real-time processing of complex data, such as images, audio, and sensor inputs. Consider the implications of such a system in an age where the demand for faster, smarter, and more energy-efficient devices is ever increasing. Where every milliwatt saved translates into longer battery life for mobile devices, lower operational costs for data centers, and a smaller environmental footprint. And this is exactly what neuromorphic computing strives to achieve by taking cues from the brain's own strategies. The human brain, which operates on roughly 20 watts of power, less than many household light bulbs, manages to perform tasks that are immensely complex, from recognizing faces in a crowd to processing language and making split-second decisions, all with an efficiency that modern computers, despite their raw processing power, can barely dream of matching. And neuromorphic computing seeks to replicate this efficiency by implementing hardware architectures that mirror the brain's highly parallel structure, where each neuron processes information locally and only communicates with other neurons when an event occurs, rather than constantly polling for data. And this asynchronous event-driven model allows neuromorphic chips to scale gracefully, handling vast amounts of information without a corresponding increase in power consumption, a feat that traditional computing architectures struggle with due to their inherent need to synchronize and process instructions in a sequential manner. One of the core reasons neuromorphic systems are so energy efficient is that they rely on sparse coding, a technique inspired by the brain's ability to represent information using a small number of active neurons at any given time. And in neuromorphic hardware, this means that only the neurons that detect significant changes or features in the data will fire, while the rest remain inactive, thereby avoiding the constant energy drain associated with traditional processors that operate on a continuous clock cycle regardless of the workload. And by harnessing this principle, neuromorphic chips can process sensory inputs such as visual data from cameras or auditory signals from microphones in a way that is not only fast but also remarkably power conserving, a critical advantage in applications like autonomous vehicles, drones, or wearable devices where energy efficiency is paramount and every joule of power counts. Furthermore, the architecture of neuromorphic systems is inherently designed to maximize speed through massive parallelism, meaning that instead of relying on a single powerful processor to perform sequential calculations, these systems distribute the computational load across an extensive network of artificial neurons that work concurrently, enabling rapid pattern recognition and decision-making processes that occur in real time. And this parallel processing capability is particularly beneficial in scenarios where speed is crucial, such as in real-time sensory processing for robotics, where a machine must analyze and respond to its environment almost instantaneously, or in high-frequency trading systems, where milliseconds can mean the difference between profit and loss. And the ability to process data in parallel not only accelerates computations, but also allows for more complex models and algorithms to be run efficiently, all while keeping power consumption low. In addition to their parallel processing prowess, neuromorphic systems also employ advanced techniques like spiking neural networks, where information is transmitted through discrete pulses, or spikes, rather than continuous signals. And this mode of communication is remarkably similar to how biological neurons operate, transmitting information only when a certain threshold is reached, which further contributes to energy savings because the system does not expend power continuously, but only in response to meaningful inputs. And this spiking behavior, combined with adaptive learning mechanisms that adjust the strength of connections between neurons based on the frequency and timing of spikes, a process analogous to synaptic plasticity in the brain, allows neuromorphic chips to not only operate more efficiently, but also to learn from their environment, adapt to new patterns, and optimize their performance over time, all while using power in a highly judicious manner. The implications of energy efficiency and speed in neuromorphic computing extend far beyond the realm of academic interest. as they have the potential to revolutionize a wide range of industries and applications, from consumer electronics to industrial automation, healthcare, and beyond. And consider the impact on wearable technology, where battery life is a constant challenge, and the integration of neuromorphic chips could lead to smart devices that not only last significantly longer on a single charge, but also offer enhanced functionalities like real-time health monitoring, personalized feedback, and adaptive interfaces that respond to the user's environment and behavior, all while consuming minimal energy, thereby providing a user experience that is both seamless and sustainable. Moreover, in the field of autonomous systems such as self-driving cars and drones, the combination of energy efficiency and speed provided by neuromorphic computing is particularly valuable, as these systems require the ability to process vast amounts of sensor data from cameras, LiDAR, radar, and other sources in real time, make instantaneous decisions, and adapt to rapidly changing environments. And the brain-inspired architecture of neuromorphic chips enables these vehicles to operate with a level of responsiveness and power efficiency that traditional computing systems struggle to achieve, potentially leading to safer, more reliable, autonomous navigation systems that can operate continuously for extended periods without the need for frequent recharging or high-powered cooling systems. In the realm of data centers and cloud computing, where energy consumption is a major cost and environmental concern, neuromorphic computing offers a compelling solution by dramatically reducing the power required to perform complex computations. And as data centers continue to grow in size and complexity, the need for energy-efficient hardware becomes increasingly critical, not only to reduce operational costs, but also to mitigate the environmental impact of massive computational infrastructures, and by incorporating neuromorphic architectures that mimic the brain's ability to process information in a parallel and event-driven manner. Data centers could achieve higher computational throughput with significantly lower energy bills, thereby making large-scale computing more sustainable and cost-effective. The energy efficiency and speed of neuromorphic systems also open up exciting possibilities in the field of artificial intelligence, where the demand for real-time processing of massive data sets is constantly increasing, and traditional deep learning models, while powerful, often require enormous amounts of energy and computational resources to train and deploy. But neuromorphic computing offers a new paradigm in which AI models can be run on hardware that is not only faster, but also far more energy efficient, enabling a range of applications that were previously impractical, such as in real-time language translation, smartphones, real-time language translation, adaptive robotics, and interactive virtual environments. And this shift has the potential to democratize access to advanced AI capabilities by reducing the barriers to entry associated with high-powered computing, allowing smaller companies and even individual researchers to develop and deploy sophisticated AI models without the need for massive energy-hungry data centers. Additionally, the design principles underlying neuromorphic computing challenge the conventional wisdom of processor design, which has been dominated by the pursuit of ever-increasing clock speeds and transistor counts. And instead, neuromorphic systems focus on a more holistic approach that prioritizes energy efficiency, scalability, and real-time performance. And this rethinking of processor architecture is not just a minor tweak. It represents a fundamental shift in how we conceive of computation, one that draws inspiration from billions of years of biological evolution and the elegant solutions that nature has developed to process information with remarkable efficiency. And by embracing these principles, engineers and scientists are paving the way for a new generation of computing systems that are better suited to meet the demands of modern applications, where power, speed, and adaptability are the keys to success. In practical terms, the development of neuromorphic chips involves the integration of novel materials and fabrication techniques that support the dynamic, adaptive behavior of artificial neurons, such as memristors, which can mimic the variable resistance of biological synapses. And these devices are designed to store and process information simultaneously, eliminating the bottlenecks associated with the traditional separation of memory and processing found in von Neumann architectures. And this integration is crucial for achieving the low power consumption and high speed that neuromorphic systems promise, as it allows for faster data transfer, reduced latency, and more efficient use of available energy, all of which contribute to a computing platform that operates in a manner that is both intuitive and in harmony with the natural world. The promise of neuromorphic computing's energy efficiency and speed is also being demonstrated in a range of experimental applications and prototypes, from smart sensors that can analyze environmental data in real time, to advanced robotic systems that use neuromorphic processes to navigate complex terrains and respond to unpredictable challenges. And these early successes are fueling further research and development as scientists and engineers work to refine the technology, improve its scalability, and integrate it into a broader range of applications. And each breakthrough brings us closer to a future where neuromorphic systems are a common feature in everything from consumer devices to industrial automation, transforming the way we interact with technology and enabling a level of performance that is both unprecedented and sustainable. As we look ahead, the continued evolution of neuromorphic computing holds the promise of even greater advancements in energy efficiency and speed as researchers explore new architectures, refine learning algorithms, and develop innovative ways to mimic the brain's natural processing abilities. And with each step forward, the gap between biological intelligence and artificial systems narrows, paving the way for a future where computers not only think faster and more efficiently, but also learn, adapt, and evolve in ways that mirror the human experience, creating a synergy between man and machine that was once the stuff of science fiction and now stands as a tangible, rapidly emerging reality. In this future, the implications of energy-efficient and high-speed neuromorphic systems will ripple across every facet of society, from the personal devices that connect us to the global networks that drive our economies. And the benefits will extend beyond mere performance improvements to encompass environmental sustainability, cost reductions, and a new era of innovation that redefines what it means to compute. And as we continue to harness the principles of neuroprocessing, we are not only building faster, smarter machines, but also setting the stage for a revolution in how technology integrates with our lives, offering tools that are more responsive, intuitive, and aligned with the rhythms of the natural world. The journey toward fully realizing the potential of neuromorphic computing is ongoing. And while challenges remain in terms of scaling up these systems, ensuring robustness, and integrating them with existing technologies, the strides made so far are a testament to the power of brain-inspired design, and they underscore the transformative impact that energy efficiency and speed can have when achieved through architectures that are modeled on the human brain, where every synaptic adjustment and every parallel computation is a step toward a more efficient, intelligent, and sustainable future, one in which the computational demands of tomorrow are met not by brute force, but by a delicate balance of power and precision that mirrors the elegance of nature itself. As we stand on the brink of this new era, it becomes clear that the future of computing is not about scaling up power at any cost, but about rethinking the very foundations of how we process information. And neuromorphic computing, with its focus on energy efficiency and speed, offers a compelling blueprint for a world where technology is both powerful and sustainable, where the devices we rely on every day operate with the fluidity and grace of the human brain, and where the relentless pursuit of performance does not come at the expense of our planet's resources, but rather works in harmony with them to create a future that is as promising as it is responsible. Ultimately, the promise of neuromorphic computing lies in its ability to redefine the relationship between energy and computation, to demonstrate that high performance does not have to be synonymous with high power consumption, and to show that by taking inspiration from the most efficient processor known to us, the human brain, we can build systems that not only push the boundaries of what is technologically possible, but do so in a way that is sustainable, adaptive, and remarkably fast. And as this technology matures, its influence will extend far beyond the confines of research labs, permeating every aspect of our digital lives, transforming industries, enhancing everyday devices, and ushering in an era where the fusion of biology and technology becomes the new standard for innovation, efficiency, and speed. Adaptive learning and real-time processing. Neuromorphic computing is transforming the landscape of technology by incorporating the principles of adaptive learning and real-time processing into its very core, a transformation that redefines the way machines learn, react, and evolve. Imagine a system that doesn't rely on rigid, pre-programmed instructions, but instead continuously learns from its environment, adapts to new data as it comes in, and makes decisions on the fly, much like the human brain, where every sensory input and experience shapes our understanding and behavior in real time. Neuromorphic platforms are built to support learning algorithms that are not static but fluid, designed to adjust and refine themselves with every new piece of information they encounter. And it is this adaptive quality that makes them ideally suited for applications in artificial intelligence, robotics, and autonomous systems that require continuous learning and rapid decision-making. Consider, for instance, an autonomous robot navigating a dynamic environment where conditions can change in an instant. A pedestrian suddenly appears, the terrain shifts, or unexpected obstacles emerge. In traditional computing systems, the robot might rely on pre-programmed routines and static algorithms, which can quickly become outdated or insufficient when faced with unforeseen circumstances. In contrast, a neuromorphic system, inspired by the adaptive learning processes of biological neural networks, is capable of processing sensory data in real time, updating its internal models on the fly, and adapting its behavior almost instantaneously to new conditions. This is achieved through the use of spiking neural networks that emulate the way neurons in the brain communicate via discrete electrical pulses, allowing the system to not only recognize patterns, but also to learn from every interaction with its environment. As the robot moves through its surroundings, its neuromorphic processor continuously adjusts the weights of its artificial synapses based on the incoming stimuli, refining its decision-making process with every new piece of data, and thereby creating a level of responsiveness and adaptability that is far beyond the reach of conventional computing architectures. At the heart of this capability is the concept of real-time processing, where the system operates in an event-driven manner, rather than relying on clock cycles that force it to process information in a predetermined sequence. In the human brain, neurons remain in a resting state until stimulated by a significant event, and then they fire to transmit information across networks, a process that is both highly efficient and incredibly fast. Neuromorphic systems replicate this behavior by designing circuits that remain dormant until activated by relevant inputs, thereby conserving energy and allowing for rapid processing when required. This means that the system is not bogged down by constantly processing irrelevant data or executing redundant calculations, but instead it springs into action only when necessary, ensuring that computational resources are focused on the most critical tasks at any given moment. The result is a system that can handle vast amounts of information with remarkable speed, a feature that is particularly important in fields such as autonomous vehicles and robotics, where the ability to respond in real time can be the difference between a safe operation and a catastrophic failure. This adaptive learning is not a one-time process. It is a continuous cycle of observation, analysis, and adjustment that enables the system to evolve over time. In traditional machine learning, models are often trained offline on large data sets and then deployed in a fixed state, unable to incorporate new data until the next training cycle. Neuromorphic platforms, however, are designed for online learning, meaning they can update their internal models in real time as they interact with their environment. This is achieved through mechanisms akin to synaptic plasticity, the biological process by which the strength of connections between neurons is adjusted based on experience. In a neuromorphic system, artificial synapses change their weights continuously as new data is received, allowing the system to learn from its successes and mistakes, refine its predictive accuracy, and adapt to new patterns as they emerge. Over time, this leads to a system that becomes increasingly efficient at performing its designated tasks, whether that is recognizing complex visual patterns, interpreting natural language, or controlling the movement of a robot in an unpredictable environment. One of the most compelling aspects of adaptive learning in neuromorphic computing is its ability to deal with uncertainty and incomplete information. In many real-world scenarios, data can be noisy, ambiguous, or only partially available, and traditional computing systems often struggle to make sense of such information in a timely manner. Neuromorphic systems, on the other hand, are designed to be robust in the face of uncertainty, much like the human brain, which is capable of making decisions based on limited or imperfect data. By continuously updating their internal representations and employing probabilistic methods, neuromorphic processors can effectively filter out noise, extract meaningful patterns, and make informed decisions even when the input is less than perfect. This resilience is critical in applications such as medical diagnosis, where sensor readings may be affected by various external factors, or in autonomous navigation, where environmental conditions can change rapidly and unpredictably. The ability to learn and adapt in real time not only improves the accuracy of the system's responses, but also enhances its overall reliability and robustness. Furthermore, adaptive learning in neuromorphic systems enables a form of personalization and contextual awareness that is unparalleled in traditional computing paradigms. Consider a smart home environment where a neuromorphic device is tasked with managing energy consumption, adjusting lighting, and controlling climate settings based on the habits and preferences of its inhabitants. Rather than operating on a fixed schedule or reacting to predefined triggers, the neuromorphic system can observe patterns over time, learning when residents typically arrive home, how temperature preferences shift with the seasons, and even how external factors like weather affect indoor comfort. It can then dynamically adjust its operations to optimize energy usage, improve comfort, and even predict future needs, creating an environment that is not only efficient but also highly responsive to the individual patterns of its users. This level of adaptive personalization, achieved through real-time processing and continuous learning, exemplifies the transformative potential of neuromorphic computing in creating systems that are deeply integrated with human lives. In the realm of artificial intelligence, adaptive learning and real-time processing are the cornerstones of creating truly intelligent systems that can operate autonomously in complex changing environments. Traditional AI systems, while powerful in control settings, often require massive computational resources and extensive offline training to achieve high levels of performance, and they tend to falter when confronted with novel situations that were not present in their training data. Neuromorphic platforms, by contrast, are inherently designed to be flexible and dynamic, capable of learning from new experiences without the need for extensive retraining. This makes them particularly well suited for applications in robotics and autonomous systems, where the ability to adapt to new situations in real time is critical. For example, an autonomous drone equipped with a neuromorphic processor can continuously update its flight path based on real-time sensor inputs, adapting to wind conditions, obstacles, and changing mission parameters with a level of agility and responsiveness that would be impossible with conventional computing architectures. Similarly, in industrial automation, robots powered by neuromorphic chips can learn to optimize their movements and tasks on the fly, improving efficiency and reducing errors in dynamic production environments. Adaptive learning also plays a crucial role in the field of natural language processing, where the ability to interpret and generate human language requires not only the processing of vast amounts of data, but also the capacity to understand context, nuance, and intent. Neuromorphic systems, with their real-time processing capabilities, can facilitate more natural and responsive interactions between humans and machines. Imagine a virtual assistant that learns from each interaction, adapting its responses to better match the user's communication style and preferences, and that can update its understanding of context as conversations evolve. Such a system would not be limited by the static, rule-based algorithms of traditional chatbots, but would instead offer a more fluid, human-like interaction, capable of understanding subtle shifts in tone, context, and meaning in real time. This level of adaptive interaction is essential for the development of next-generation AI applications that require a deep understanding of human communication. The benefits of adaptive learning extend to domains such as finance and trading as well, where real-time data processing and continuous adaptation can provide a significant edge in highly volatile markets. In these applications, neuromorphic systems can analyze streams of market data, learn from patterns of behavior, and adjust trading strategies in real time, all while operating within strict energy constraints and delivering rapid response times. By continuously refining their internal models based on live market conditions, these systems can make more informed decisions, reduce risk, and capitalize on fleeting opportunities that might otherwise be missed by traditional, slower algorithms. The capacity for real-time adaptation is particularly valuable in such fast-paced environments where even a slight delay in processing or decision-making can have significant financial implications. In practical terms, implementing adaptive learning and real-time processing in neuromorphic hardware involves a careful balance between hardware design and algorithmic innovation. Engineers must develop circuits that not only replicate the behavior of neurons and synapses, but also do so in a manner that is both scalable and energy efficient. This often involves the use of cutting-edge materials and novel device architectures such as memristors, which are capable of storing analog values and adjusting their resistance based on the history of electrical signals they have received, much like the way synapses in the brain strengthen or weaken over time. These devices, when integrated into a neuromorphic chip, provide the physical substrate for adaptive learning, enabling the chip to dynamically adjust its internal parameters without the need for external intervention or reprogramming. The evolution of adaptive learning and real-time processing in neuromorphic computing is also driving a paradigm shift in the way we approach artificial intelligence, moving away from static models and towards systems that are capable of lifelong learning. Traditional AI models are typically trained on vast amounts of data in a controlled environment and then deployed with fixed parameters, which limits their ability to adapt to new information once they are in operation. Neuromorphic systems, by contrast, are designed to evolve continuously, incorporating new data as it becomes available and adjusting their internal models accordingly. which not only enhances their performance, but also allows them to operate effectively in environments that are constantly changing. This dynamic approach to learning means that neuromorphic platforms have the potential to overcome one of the key limitations of current AI systems, their inability to adapt to novel, unforeseen circumstances without undergoing a lengthy retraining process. The integration of adaptive learning and real-time processing in neuromorphic platforms also has profound implications for the future of human-machine interaction, as these systems are poised to create a new generation of devices that are more intuitive, responsive, and context-aware than ever before. Imagine smart devices that do not simply respond to preset commands, but instead learn from your behavior, anticipate your needs, and adapt their functions to suit your lifestyle, all in real time. Such systems could transform everything from personal assistance and home automation to industrial control systems and interactive entertainment, ushering in an era where technology seamlessly integrates with our daily lives, becoming not just tools, but partners that evolve alongside us. As researchers continue to push the boundaries of what is possible with neuromorphic computing, the emphasis on adaptive learning and real-time processing is only expected to grow, driving innovations that could one day lead to machines capable of complex reasoning, creative problem solving, and even forms of emergent intelligence that mimic the depth and adaptability of the human mind. The ongoing convergence of neuroscience, material science, and computer engineering is laying the groundwork for these breakthroughs. As scientists work to unravel the mysteries of the brain's learning processes and translate them into algorithms and hardware that can perform at scale, efficiently, and in real time. In summary, the adaptive learning and real-time processing capabilities of neuromorphic platforms are not merely incremental improvements over traditional computing. They represent a fundamental rethinking of how machines learn, process information, and interact with the world, drawing direct inspiration from the most sophisticated learning system we know, the human brain. By enabling systems to continuously update their internal models based on real-time data, adapt to new patterns without the need for offline retraining, and process complex sensory information with unparalleled speed and energy efficiency, neuromorphic computing is poised to revolutionize a wide array of applications, from autonomous vehicles and robotics to AI-driven healthcare and beyond, ultimately paving the way for a future where intelligent systems are not just powerful, but also inherently adaptive, resilient, and in tune with the dynamic nature of the world around them, potential for future AI breakthroughs. Imagine, for instance, an AI system that is not constrained by the linear, sequential processing of traditional computers, but instead operates like the human brain, where millions of interconnected artificial neurons and synapses work simultaneously in parallel, processing complex information streams with a level of speed and efficiency that has until now remained out of reach. And consider the profound implications of such a system for machine learning, where the ability to learn from new data in real time without requiring lengthy retraining cycles could lead to algorithms that continuously improve and adapt to changing environments, recognize subtle patterns in massive data sets almost instantaneously, and make decisions that are both rapid and remarkably context-aware, ultimately revolutionizing industries that rely on predictive analytics, autonomous decision-making, and real-time responsiveness. From self-driving cars and industrial automation to healthcare diagnostics and personalized user experiences. Neuromorphic systems, by emulating the brain's ability to handle sparse, event-driven data through spiking neural networks, offer a level of energy efficiency that is unparalleled in conventional computing architectures, which often require enormous amounts of power to process even a fraction of the information that a human brain can manage on just 20 watts. And this energy efficiency is critical, not only for reducing the operational costs of data centers and cloud computing infrastructures, but also for enabling the deployment of sophisticated AI applications in portable, battery-powered devices such as smartphones, wearable gadgets, and even remote sensors, where power is at a premium and every milliwatt saved translates into longer operational times and reduced environmental impact. And it is this remarkable combination of low power consumption and high-speed processing that sets neuromorphic computing apart, making it ideally suited to support the next generation of AI breakthroughs that demand both agility and sustainability. Moreover, the capacity for neuromorphic systems to perform cognitive tasks in a way that closely mimics the human brain's own method of processing sensory information means that these platforms are uniquely positioned to drive advancements in cognitive computing, where machines are not simply following rigid instructions, but are instead capable of reasoning, adapting, and even exhibiting forms of creativity that were once thought to be the exclusive domain of biological organisms. And this shift has the potential to transform the very nature of human-machine interaction, paving the way for intelligent systems that can understand context, interpret ambiguous data, and provide insights that are both deep and actionable, thereby enhancing our ability to make sense of complex data sets, predict future trends, and solve problems that are as varied as they are challenging. Imagine a scenario in which an AI-powered healthcare system, equipped with neuromorphic processors, continuously monitors a patient's vital signs, learns from subtle changes in physiological data in real time, and predicts potential health issues before they become critical, enabling early intervention and personalized treatment plans that can save lives. And envision how such a system, operating with the speed and efficiency of a neuromorphic chip, could analyze thousands of medical images in seconds, detect anomalies that might elude even the most experienced human eyes, and adapt its diagnostic criteria based on new research and real-world outcomes, thereby transforming the field of medical diagnostics into one that is not only more accurate and efficient, but also more accessible to people around the world, regardless of their geographic or economic circumstances. The potential for future AI breakthroughs extends well beyond healthcare, reaching into every domain where data is generated, processed, and acted upon. And neuromorphic computing stands at the forefront of this revolution, offering the promise of real-time data analytics that can keep pace with the ever-growing volume and complexity of information in today's digital age. And in industries like finance, where market conditions can change in the blink of an eye, neuromorphic systems could enable algorithms that detect emerging patterns and anomalies almost instantaneously, allowing traders to make informed decisions faster than ever before. And in the realm of cybersecurity, these systems could analyze network traffic in real time, identify potential threats, and adapt their defense mechanisms dynamically, thus providing a level of protection that is both proactive and responsive, far surpassing the capabilities of static, rule-based systems. The breakthrough potential of neuromorphic computing in the context of AI is not limited to speed and efficiency alone. It also lies in the inherent adaptability and resilience of these systems, which are designed to continuously learn from new data, adjust their internal parameters based on feedback, and evolve their processing strategies in response to changing conditions. Much like the way the human brain forms new neural connections and reorganizes itself in response to new experiences, a process known as neuroplasticity. And this ability to adapt is particularly crucial in environments where the data is not only vast but also unpredictable and non-stationary, such as in natural language processing, where the meaning of words and the context of conversations can shift rapidly, or in autonomous systems that must navigate complex, dynamic environments without the benefit of pre-programmed instructions. Neuromorphic systems employ learning algorithms that are fundamentally different from traditional machine learning techniques. leveraging the concept of unsupervised learning to allow the system to identify patterns and relationships in data without explicit human guidance. And this means that as these systems are exposed to new information, they can update their models in real time, improving their accuracy and performance and the result is an AI that is not static, but is constantly evolving, capable of dealing with uncertainty, adapting to new challenges, and even discovering novel solutions to problems that were previously deemed intractable by conventional methods. And it is this dynamic, self-improving nature that holds the key to many of the future breakthroughs we can expect in the field of AI. Consider the implications of such adaptive intelligence in the realm of robotics, where a neuromorphic processor could enable a robot to learn from its environment, adjust its behavior based on real-time feedback, and navigate complex terrains with an agility that mimics biological organisms. And imagine how this level of autonomy could lead to robots that are capable of performing intricate tasks in unpredictable settings, whether it's exploring distant planets, assisting in disaster relief efforts, or performing delicate surgical procedures, with a level of precision and responsiveness that outstrips the best of today's technology. And in doing so, neuromorphic systems will not only revolutionize robotics, but also redefine our expectations of what machines can achieve, bridging the gap between artificial and human intelligence in ways that were once the realm of science fiction. The integration of neuromorphic computing with AI also opens up exciting possibilities for cognitive computing, where systems are designed to emulate human thought processes, understand natural language, reason logically, and even exhibit a form of creativity. And by harnessing the energy efficiency, speed, and adaptive learning capabilities of neuromorphic architectures, cognitive computing platforms can process vast amounts of unstructured data, such as text, images, and sound, at a pace that enables real-time interaction and decision-making. And this could transform industries such as customer service, where intelligent virtual assistants provide personalized support by understanding and responding to queries in a human-like manner, or education, where adaptive learning systems tailor content to the individual needs of students, thereby enhancing the learning experience and outcomes. Moreover, neuromorphic systems have the potential to fundamentally alter the design of AI hardware, moving away from the traditional, power-hungry architectures that rely on large data centers and cloud computing, and instead paving the way for distributed, edge-based AI solutions that bring intelligence closer to where the data is generated, thereby reducing latency, enhancing privacy, and enabling applications that require instantaneous processing and decision-making, such as augmented reality, smart city infrastructure, and real-time environmental monitoring. And as these edge devices become more intelligent and capable, we can envision a future where the power of AI is democratized, accessible not only to large corporations, but also to small businesses and individual users, fostering an ecosystem of innovation that is both decentralized and inclusive. The future of AI breakthroughs enabled by neuromorphic computing is also intrinsically linked to advances in material science and microfabrication techniques, as researchers work tirelessly to develop chips that can mimic the complex, adaptive, and energy-efficient behavior of biological neural networks. And these efforts have already led to promising prototypes and experimental platforms that demonstrate the feasibility of integrating neuromorphic processes into a wide range of devices, from smartphones and laptops to autonomous vehicles and industrial robots. And as these technologies mature, we can expect to see a convergence of AI, neuromorphic hardware, and other emerging fields such as quantum computing, further accelerating the pace of innovation and enabling applications that are beyond the reach of today's classical systems. In this emerging landscape, the potential for future AI breakthroughs is not merely about incremental improvements in processing power or efficiency, but about a fundamental rethinking of what artificial intelligence can be, how it learns, and how it interacts with the world. And neuromorphic computing, with its brain-inspired design and adaptive learning capabilities, offers a paradigm shift that could lead to AI systems that are more resilient, intuitive, and capable of generalizing their knowledge across a wide range of tasks, much like a human being who can apply learned skills in novel situations. And this level of versatility and adaptability is the holy grail of AI research, promising a future where machines are not only tools that execute commands, but partners that collaborate with humans, understand our needs, and help us solve some of the most complex challenges facing society today. The revolution brought about by neuromorphic computing in the realm of AI is poised to transform industries in ways that we can only begin to imagine, from healthcare and transportation to finance, education, and beyond. And as AI systems become more intelligent, responsive, and energy efficient, they will drive innovations that lead to smarter, safer, and more sustainable solutions, revolutionizing the way we live and work, and fundamentally reshaping the economic and social landscapes of our world. And as we look to the future, the convergence of neuromorphic hardware with advanced AI algorithms promises to create systems that are capable of learning continuously, adapting seamlessly, and operating in real time, heralding a new era of technological breakthroughs that push the boundaries of human ingenuity. In summary, the potential for future AI breakthroughs through neuromorphic computing is vast and far-reaching, driven by the unique ability of these systems to handle massive amounts of data, perform cognitive tasks naturally, and continuously learn and adapt in real time. A combination of features that promises to revolutionize machine learning, cognitive computing, and real-time data analytics, thereby unlocking new levels of performance and intelligence that will define the next generation of artificial intelligence. And as researchers continue to innovate, refine, and scale these brain-inspired architectures, we are on the cusp of a transformative shift that will not only redefine our technological capabilities, but also reshape our very understanding of intelligence, ushering in an era where the synergy between human-like cognition and machine efficiency creates a future of unprecedented possibility, where AI systems are more than just computational tools. They become dynamic, intelligent collaborators, capable of solving the complex, ever-evolving challenges of our world. And it is in this vision of a smarter, more adaptive, and energy-efficient future that the true promise of neuromorphic computing for AI breakthroughs lies.